All right, welcome to The Explainer. Today we are jumping headfirst into one of the deepest, most mind-bending mysteries in all of science. We're going to be exploring the very fabric of reality itself, a place where our very best theories just completely and utterly break down. And you know what? It all starts with a simple question about the most common thing in the entire universe. Nothing.
It sounds like a riddle, right? What is nothing? For most of human history, the answer seemed pretty obvious. Nothing is emptiness, a void. It's just the complete absence of stuff. But as we're about to see, modern physics has totally demolished that simple idea and replaced it with something far, far stranger, way more active, and profoundly more mysterious.
So, to really get this, let's put the old idea right next to the new one. For centuries, we pictured a vacuum as a perfectly empty box, a passive, silent, boring backdrop for the universe. But the quantum view? It's the exact opposite. It tells us that what we call empty space is actually the seething sea of energy, constantly active, even when it's in its lowest possible energy state. To unravel this whole thing, we're going to follow the clues like a cosmic detective story. First, we'll bust the myth of emptiness. Then, we'll look for the evidence that proves the void is actually hyperactive. We're going to measure its energy on a cosmic scale, which, believe it or not, leads us straight into something called the vacuum catastrophe, the biggest disagreement in all of physics. Then we'll join the hunt for answers, and finally, we'll have to face the ultimate question this whole mystery forces us to ask: what is reality really?
Okay, so our investigation starts with this really revolutionary idea that just rewrites all the rules: quantum field theory.
So in modern physics, everything you see, electrons, photons, you, me, it's all just an excitation, like a ripple in some kind of underlying field. The quantum vacuum is just what's left when all those fields calm down to their absolute lowest energy level. But here's the catch. Calm does not mean still. The vacuum is constantly buzzing with these energy fluctuations, creating what we call virtual particles. They're like these fleeting ghosts of matter and energy that pop in and out of existence faster than you can even imagine. They're real enough to have an effect, but they're too brief to ever be caught.
Okay, so this idea of a hyperactive void, it's pretty fascinating, but is it real? Can we actually prove it? Well, it turns out this is not just some theoretical fantasy. This background energy has real, measurable effects on the world all around us.
This energy comes from a core rule of the quantum world, the Heisenberg uncertainty principle. At its heart, it's like a cosmic law against perfect stillness. So a quantum system, say a tiny little pendulum, can never hang perfectly motionless. It must always jitter with some minimum amount of energy. Now imagine an infinite collection of these tiny oscillators, all jittering at once. That's the quantum vacuum, and it fills all of space with this baseline hum of energy. A cosmic hum of energy is a really cool concept, but if these virtual particles are like ghosts, how can we possibly prove they're there? Is there any way to actually measure the force of nothing?
Amazingly, yes, there is. An incredibly clever experiment called the Casimir effect is the smoking gun. Here's the idea. You take two uncharged metal plates and you put them incredibly close together inside a vacuum. When you do, a real physical force actually starts pushing them together. So why does this happen? Well, because that tiny space between the plates restricts the kinds of virtual particles that can pop into existence there. But the huge space outside has no restrictions at all. And that energy difference creates a real measurable pressure.
And this is not just a theory anymore. Back in 1996, scientists finally measured this tiny force, and you know what? The results match the predictions perfectly. We can literally measure the force of the quantum vacuum. It is absolutely real.
So we've confirmed a vacuum has energy on a tiny microscopic scale in a lab. Now let's zoom out. I mean, way, way out, all the way to the scale of the entire universe. Can we measure the energy of empty space out there?
Turns out we can. By observing that the expansion of the universe is actually accelerating, astronomers have been able to calculate the energy density of space. They call this mysterious force dark energy, and its value, the cosmological constant, is absolutely minuscule. I mean, it is incredibly close to zero. But, and this is the crucial part, it's not zero.
All right, the stage is set. We've got our observation from cosmology, this tiny, almost zero energy. And we have our theory, quantum field theory, which predicted that Casimir effect so perfectly. So now let's just ask our theory to predict the number we just saw from the cosmos. And this is where the story takes a dramatic, catastrophic turn.
This
This is what quantum field theory predicts for the energy density of the vacuum. That's not a small number. It is the most absurdly, unimaginably enormous number in all of science. The theory that works perfectly on small scales gives us this monstrosity when we apply it to the cosmos.
This colossal disagreement, this chasm between the observed value and the theoretical prediction, it's famously known as the vacuum catastrophe. And that is not an exaggeration. It is the single greatest crisis in modern fundamental physics.
And let's be clear, this isn't just a small mistake. The prediction is wrong by 122 orders of magnitude. That is, a 1 followed by 122 zeros. To put that in perspective, that's like trying to measure the width of North America and being off by less than the width of a single atom. Something is profoundly, deeply wrong with our understanding of the universe.
So what on earth is going on? Well, physicists are on the hunt, trying to solve this mystery. One of the big ideas is that at the tiniest possible scales, spacetime itself isn't smooth, but it's actually this jittery, fluctuating foam of energy. And they've designed some incredible experiments to go looking for it.
And there are two main strategies. On one hand, you've got telescopes like NASA's, looking at light that has traveled for billions of years from distant quasars. The thinking is, if space-time is foamy, that light should get blurred over its long journey. And on the other hand, you've got Fermilab's holometer, this incredibly sensitive device designed to detect tiny local jitters or twists in spacetime, right here on Earth.
So what did NASA find? Well, after observing the most distant objects in the universe, they found the images were crystal clear. There was no blurring at all. The message from the cosmos was pretty unambiguous. On the largest scales, space-time is incredibly smooth, way calmer than some of those quantum foam theories suggested.
Okay, so the universe is calm on the grand scale. But what about up close? What about those high-frequency jitters that Fermilab was listening for? I mean, their experiment was sensitive enough to detect motion 1,000 times smaller than a proton. So what did they find? The research team's conclusion was as simple as it was profound. After years of listening for the roar of quantum spacetime, they heard nothing. As one of the scientists put it was quiet. Even at the most fundamental level we can currently probe, the fabric of reality appears to be astonishingly still.
And this brings us to this really bizarre conclusion. Our most successful theory in physics is screaming that the vacuum should be a chaotic storm of energy. But every single observation we make, from the edge of the visible universe to a tabletop in a lab, tells us that it's almost perfectly serene.
This is the absolute heart of the vacuum catastrophe. It's not just some numerical error, it is a fundamental contradiction about the nature of reality. And the weirdest part is that the experimental results, by finding nothing, have only made the theoretical problem even more profound. There is a huge piece of this puzzle missing, and we have no idea what it is.
And so we end right back where we began, with a question. If our best theories suggest that the energy locked away in nothing is exponentially greater than all the matter in all the galaxies combined, what does that really say about something? About the stars, the planets, you and me? It suggests that the calm, stable universe we experience is balanced on an extraordinary, energetic knife's edge that we are only just beginning to comprehend.